Hi, I'm Joonhyung Kim, and this is the third oral presentation for Fourier optics. I'm going to explain the solution of problems from Fourier optics chapter 4 and 6. This presentation is divided into 4 sections. These are contents of my presentation. First, I'll briefly explain the Fraunhofer diffraction and move on to the problem of chapter 4. Then we will check the basic relationship of optical imaging system and solve the problem number 6 together. In section 3, I'll explain some more information about coherent and incoherent imaging system. Lastly, we are going to look at the summary of results. Before we enter the problem of Fraunhofer diffraction, let's check the concept of diffraction. If there is an aperture with blocked center, we can easily imagine the central image plane would be dark. But the center is rather brightest region of image plane at Fraunhofer diffraction situation. We had seen the double slit diffraction many times. We know the secondary waves originating from two slits make interference pattern. In case of Fraunhofer diffraction, the viewing screen and the aperture are separated by a large distance. As the separation increases, the size of the pattern changes but not its shape. In case of circular aperture, we can get special diffraction pattern called Airy pattern. The normalized intensity is shown here. Now let's check the problem number 10. We had to get intensity distribution in the Fraunhofer diffraction pattern in case of ring aperture. And in Fraunhofer diffraction, we have to assume that the input light must be unit amplitude plane wave. The numerical solution of this problem is like this. First, we set the amplitude transmittance function for the ring-shaped aperture. And because this aperture is circular symmetry, this equation can be applied for Fourier-Bessel transform. Fraunhofer diffraction pattern can be written function of u, and the intensity function is squaring the absolute value of u. This is MATLAB solution of this problem. WO and WI are outer and inner circle radius. Function of g represents amplitude transmittance function. I used the circle shape for circle function. G1 is amplitude transmittance function for outer circle and G2 is for inner circle. G1 minus G2 is total amplitude transmittance function. Figure 1 is aperture image. We can get the Fraunhofer diffraction pattern use FFT shift in MATLAB. The image on the left side is that diffraction pattern. And I apply some code for intensity pattern in 3D image. Figure 4 is the normalized intensity of 2D Fraunhofer pattern. Let's move on to the next chapter. In chapter 6, we analyze the optical imaging system. This is the basic relationships and terminology. In current point spread function shown as H means optical fields produced when the illumination is a point source. In incurrent, point spread function shown as HI is squaring the absolute value of H, and this means intensity produced when the illumination is a point source. In case of coherent illumination system, we care about amplitude transfer function, and incoherent system, we care about optical transfer function. The problem we will solve in this case of incoherent illumination system. Let's check the problem number 6. We need to sketch the optical transfer function in different two directions. To solve this problem numerically, we set the OTF function h in fx and fy direction. OTF is the overlap area normalized by the total area of the pupil. So the figure can be achieved like this. This is MATLAB solution for this problem. I use circle shade for circle function, and total amplitude transmittance function is explain the function of G. The aperture image is well designed. We know the OTF is the overlap area normalized by the total area of the pupil. So I calculate the total area of the pupil use sum function. And for getting overlap data, I made another moving aperture that is same shape of the original. The generated aperture may move from left to right, and when they met, the area of overlap will gather and plot the graph. Let's check the video of OTF figure in fx direction. For fy direction, we should make the apertures meet each other in direction of bottom to top. But for the simple method coding, I rotated the aperture and used the same mechanism. The MATLAB code is similar with the previous code, but the result must be different, because in this case the direction is like this way. So let's check the video of OTF figure in fy direction. As we compare the numerical result and simulation result, we can decide the simulation result has some credibility. We now get back to the basic relationship and terminology of imaging system for comparing two different cases. In the coherent system, we care about optical fields, so the point spread function is just written as h. But the incoherent system, we need to analyze the imaging in terms of intensity. Here is some reference data for diffraction limit and OTF. In a diffraction limited optical system with clear rectangular aperture and no aberrations, using spatially incorrect illumination, the fringe visibility at the image of sinusoidal thin transparency of special frequency U0 decreases linearly with U0 according to the triangle function. In a diffraction limited optical system with circular aperture, the contrast decreases approximately linearly with U0 according to the autocorrelation function of the circle function. The last title is Qualitative Comparison of Spatially Coherent with Incoherent Imaging. Incoherent imaging generally gives better image quality, cause there is no ringing artifacts, no speckles, and there has higher bandwidth. But incoherent imaging is insensitive to phase objects. In case of polychromatic imaging, introduces further blurring due to chromatic aberrations. Depends on MTF of wavelengths. This is the summary of results that I made with MATLAB. I made the ring shape aperture and checked the Fraunhofer diffraction by using several ways, and plot the optical transfer function in case of incoherent imaging system. This is the end of my presentation. Thank you for listening.